Next speaker is Professor Toshihiro, and he's with the University of Tokyo. He will give a talk on autonomous platform system for underwater exploration, light for the sea, and adventure for the robot. The stage is yours.
Good morning, everyone. And thank you very much for inviting me to such an exciting conference. So I'm very excited to be here today. So firstly, I'd like to introduce myself. I'm Toshihiro Maki, Associate Professor of the University of Tokyo, and my major is underwater robotics, especially autonomous platform systems. So I know you, all of you know that the ocean survey is very important. It covers 70% of the Earth, and only 20% of the ocean has been measured. Comparing the moon, it has already surveyed 100%. So we know full shape of the moon, but we only know 20%. So but that's very important to survey the ocean. But the problem is that the ocean is deep and no radio waves, and visibility is limited, and access is also limited. So it's very difficult for us to directly survey, and remote sensing is also difficult. So that's why we developed many underwater vehicles, and you know that there are many applications that the underwater robotics are necessary. So this figure, the center figure, shows some of the examples of the underwater robots and developed up to now. So there are some robots from very shallow area to the deepest area. So I want to say that underwater robots are not a thing nice to have, but need to have, because without robots, we cannot survey the underwater things. So there is a very high demand. And I'd like to briefly explain about the types of underwater robots. So there are 3 types of vehicles. So human-occupied vehicles, and remotely operated vehicles, and autonomous underwater vehicles. And their application is also, they have some good point and weak point. So they are used to some area. So this figure shows the vertical axis is the complexity of the task in underwater. And for example, very easy task like water sampling can be done by a towfish. That's a platform that is towed by a boat. And if we attach an acoustic sonar on the towfish, then we can monitor the seafloor characteristics or bathymetry as well. But if we want to do the visual observation, like the marine corals or something, then we need robots. And currently, in many cases, we use human-controlled vehicles, because the seafloor is very complex, and we don't have good prior information about the shape and what is there, and if is there any obstacles, we don't know. So that's why we need to send a vehicle operated by humans, and we should very take care. And some extremely difficult tasks we still have to survey by ourselves. But in this case, the depth is limited. So where is the AUV? That's here. So autonomous, so that is efficient, and it's good point. But currently, the application is limited to, say, basic survey. So the goal of our laboratory is to expand the territory of the vehicles to this area. So actually, there are a lot of works happening in the world. So I'd like to introduce our research field. So our interest is underwater and autonomy. So and we are focusing on 5 points. One is multi-vehicle things. So that is a collaboration with multiple AEVs to realize wide area and high accuracy and high efficient survey of seafloor. And one is a low cost AEV. The one of the problem of AEV is that they are expensive. So they have to work by itself. So that means they have to equip good sensors in order to understand the situation. But that is also a drawback because AEV has a risk of losing because there is no tether. So one approach is that if we can realize the autonomous survey with low cost, then we can, many people will use that. And another thing is that the biological observation. So here we would like to develop an autonomous system to track and trace marine animals like sea turtle. So the project aim is to monitor the marine life. And another target is extreme environment. Here we are in collaboration with Japanese Polar Research Center, and just this year we sent our AUV to Antarctica and succeeded in the first deployment. And the other is the resident vehicle. So we have developed some seafloor station and EV to dock, so in order to extend the survey of the AVs. And one of the point of our laboratory is that we put weight on sea experiments. So we built many vehicles, so not only on simulation or tank experiments, but we put them to the ocean because the environment is very different between the tank and the ocean. So that also, of course, it's very hard, but we try to do that. So today I'd like to show some of our experiments. The first one is about the low-cost AUV system. So we developed AUV Hattori. This is a very small one. The length is about 1 meter, and the weight is about less than 20 kilograms. So that means that we can operate without crane. So the operation cost is also very low. This is very important for efficient survey. And what this vehicle can do is seafloor visual observation. So the vehicle can track rugged terrain at a low altitude, such as 1 meter or 2 meter. That's all. So this, because we wanted to make this vehicle as low cost as possible, we didn't put high level navigation sensor. So the vehicle cannot localize itself by itself. The vehicle just estimates the seafloor in front of that and navigate itself not to hit to the seafloor. So there is another vehicle. This is an ASV, autonomous surface vessel called Butri. This is this one. It's also the same size. And the aim of this vehicle is to measure the position of Hattori and follow it. So the purpose is that by deploying 2 of them, the we can get the detailed seafloor images of wide area with low cost. So this is we did some experiment at the shallow sea off the coast near Tokyo. The depth is about 20 meters. So this is the video of the vehicle. So this is top view. So, oops. So now the Hattori moves by the predefined program. So we could just follow predefined waypoints. And then the Buttori follows it and continuously measuring its position by SSBL. And this is our boat. So these two autonomous systems are surveying seafloor, and we are just watching that. After that, we obtain this kind of photo mosaic of seafloor. So the how to take this kind of zigzag trajectory, and the vehicle have a downward looking camera. So we get this kind of photo. So as the seafloor is just a sand, so not so interesting things. But anyway, we get wide area detailed survey. And then after that, we put the vehicle to the offshore volcanic island in Nishinoshima. That is about 1,000 kilometers south of Tokyo, in middle of Pacific. There's an active volcano island, and we collaboration with the environmental research institution and to see what's happening underwater. So this is the results. At surface, we operate the vehicle manually and send the autonomous diving command. After that, the vehicle do the autonomous mission. Now the vehicle start diving. We made this vehicle very highly movable, so the vehicle can directly vertically going down. So it's very, very fast diving. And the right figure shows the vehicle's perception measured by scanning sonar, and the dark area is some obstacle. In this case, seafloor. So the reflection of the sonar, and the red point. The red point is the target point where the vehicle is heading. So that we made the algorithm to generate the target point based on this data. And the left video shows the actual vehicle. So the vehicle is now following the flat seafloor. We deploy the vehicle to more complex terrain. Here, in this dive, the vehicle down the cliff. There are some complex terrain made with lava. So because it's very active, so there are some mountains and cliff. And now the vehicle is on the cliff, and so you know that sonar view, there are some steep down. So now the vehicle is going to down, following the terrain. And this down is a video of the downward looking camera. So there are some chemical things because of the heat activities. And now we know the downward of the cliff. And now the vehicle's shape is almost vertically looking down. So the downward camera is facing the surface of the cliff. And the forward camera looks the seafloor of the bottom. And then like this, the vehicle succeeded in following this complex terrain. And this is a 3D reconstruction of the cliff obtained from the dive. And actually, and another challenging thing is that there's very strong current. So this is the post-processing of the vehicle's trajectory. We noticed that the vehicle is moving sideways, but this is not the movement we intended. So this is because of the current. So because this island is a volcanic island in middle Pacific, so there are some strong and complicated flow. So what is that? Because the vehicle doesn't have good sensors, so the vehicle cannot so resist the current. But the important thing is that the vehicle was succeeded in following the terrain, not hitting. So with the suite of local sensors. And another topic is the autonomous tracking of marine life. The aim of this project is the monitoring of marine life, especially say the top level of the life, such as whales, dolphins, and turtles. So of course, there are some methods to survey them from a boat, or recently some people do biologging, so attach a tag on them, but it is very not efficient. So human have to go to the ocean and find the animal and catch it and put a tag, and then after that we have to recover the tag. But so it's very difficult. So if the vehicle, autonomous vehicle can monitor and track them without attaching anything on them, it's very efficient and whole survey can be achieved. So the idea is relatively simple. We put a mechanical, we put a multi-beam imaging sonar on the vehicle, and we developed an AI-based algorithm to detect the target on the sonar image, and then we developed the software to track the target. So this is the result of the detection. Oops. So this video was taken at a tank in aquarium, and the turtle is detected in the image. So we confirmed that in a relatively simple AI-based algorithm it also works on acoustic images. And after that, we implemented the program on the vehicle, the Hartley, and did some basic experiments. Here, the vehicle is here, and here is the sea turtle. Now the vehicle started tracking. The sea turtle is slowly swimming. Even we cannot tell the sea turtle to which movement, but that sea turtle was very collaborative, so it swam very slowly. It was very lucky. But anyway, the vehicle tracked the turtle. The reference distance is 4 meters. So the vehicle have the imaging sonar and small computer that to running the AI software. So all the processing is done in the AV. So this is the results. So this is the direction and distance to the target, the time series. So the direction is controlled within let's say probably 10 degrees, and the distance is controlled to 4 meters. So it succeeded in tracking the turtle for about 4 minutes. And after that, we are going to expand the tracking algorithm to 3D. So, and this is the latest results. So this is done by our master course student. Okay, so the final one is AUV Monaka. It's our under ice survey platform. So the Monaka is developed in the 5 years, and the aim is to obtain the shape of the ice underwater shape of the ice. Because say the Antarctica ice contains 90% of the water in the earth, and it's a very large impact on the earth. But the problem is that we don't know the exact volume of the ice. So the elevation we can measure from satellite or aircraft, but the depth of the ice is very difficult. So that's why we have to send vehicle to measure that. There are three missions. The one is the ice tracking. So follow the ice to obtain the shape of the ice. And the next one is the seafloor survey. So the under ice survey is very, it's a work for AVs because the ships, vessels cannot go there because of the ice. And also the water survey is also important. So I'd like to show you a video at the experiment. So we deployed the vehicle to
When the stakes are high at work, your tone matters. Grammarly's a
okay. So we put the vehicle to the port covered by the ice, and the vehicle tracks the waypoint. Waypoint is defined by the red circle, and looking upward looking mount beam sonar to get the bathymetry or shape of the ice. And we also have a DVL upward to relatively navigate the vehicle relative to the ice. Okay, and finally we send the vehicle to the Japanese Antarctica research cruise. It is going every year, and this time the vehicle succeeded in the first on the ice operation. So we cannot say this was 100% success, but at least we get some data that the vehicle operated on the ice. Okay, that's all. Thank you very much.